Hello everyone, May the 5th. Alright, let's finish today's challenge first. And then we are going to read the coprime separation stuff from yesterday and see what are the better solutions. I mean, my solution was now this is today's challenge. My solution was, definitely not the best, right? 9,000 milliseconds. That's bad. So we're gonna go through the discussion. But before that, let's handle this. Number of subsequences that satisfy the given sum condition. Subsequence, okay? So yesterday we said this week might be, these few days might be sliding window. So yeah, maybe a sliding window. You're given an array of integers, nums, and an integer target. Return the number of non-empty subsequences of nums such that the sum of the minimum and the maximum element on it is less than or equal to target. Since the answer may be too large, you're going to return this. Okay, so 3 5s. Let's try this. What do we have? 3, 5, 6, and 7. Okay. We want it to be less than or equal to. So 3. Oh, min and max. Got it. 3 5. 3 5 6. Oh no, it's subsequence. It's not subarray. Oh, darn. Oh, that also means we can sort it. Right? That subsequence means we can sort. So we don't have to deal with this. We can go with, oh, shoot, it's already sorted. Okay. So we can say, okay, how many, if we start with 3, right? How many we can get? If we start with 3, because 3 is the smallest, then we just need to find the largest. And these are largest, including itself. So I say, okay, I can do 3, I can do 5, I can do 6, which means I can do any combination. No. Which means target is 9, right? I just need to do 9 minus 3 is 6. So all I need is to find within this sorted array the largest possible value that is smaller or equal to 6, and it happened to be 6. So anything in this is good to go. All right. So how many different ways we can do this? Well, that's we can do 0 choose, because I can do so. Okay, 0 choose that's 2 choose 0, 2 choose 1, and 2 choose 2. Right. So this equal to 2 to the 2 equals 4. So there are 4 different ways that start with 3. Done. Okay, so start with 3, all done. Now we can say start with 5. Okay? If we start with 5, 9 minus 5 is 4. It's already smaller than we shut it. Shut is not going to happen. Let's apply it to the next one. 3, 3, 6, 8. Target is 10. Okay? So first 3, we need to find 10 minus 3 equals 7. So the largest is going to be 6. So we need to do 3 and 6. All right, that gives us 4, 2 to the 2. Next is 3. So we want to find 7 again. And we have only 1. So that's 2 to the 1, that's 2. And next one is 6. 10 minus 6 is 4. Smaller than 6, so we end it. So added together, we have 6. Good. Last one. Try the last one. 2, 3, 3, 4, 6, 7. And target is 12. So we have 12 minus 12 minus 2 is 10. So I can get the entire thing. That's 1, 2, 3, 4, 5. So it's 2 to the 5th. That's 32. Next 3, 12 minus 3 is 9. The whole thing, right? 1, 2, 3, 4. So that's 2 to the 4. That's 16. Next is 3. again, so that would be 2 to the 3, that's 8. Next is 4. Oh, that's interesting. 12 minus 4 is 8. 8, 8, 8. I only have... Oh, I have both. 2 to the 2 will be 4. Next one, 6. 12 minus 6 equals 6. Ooh, what do you do with this? Well. I think we need to search in this region then. All right, search in this region. And actually we're going to land on this, which is the same. So that's actually going to be 2 to the 0. Right? So that's going to be 1. 7 is not going to work. So add these together. What's this? 40, 48, 56, 61. 61. So it's correct. So now let's kind of think, can we make it even faster? So the current idea is we're going to do binary search. We can do binary search, but every time when we find, because we go small to large, right? So when we find the first one, we can put a pointer here, right? For this, if it's, then it's everything. If it's not, then we just search, we just go. Because this is 9, and this is 8, and this is 6. So we just search for the first one that is smaller or equal to. So I don't think we need even to do binary search. I mean, if you want, you can do binary search on the first one, but I think we can just ON the whole thing. Okay, let's try this. So first things first, we are going to sort this whole thing. Where's my mouse? Okay, so first things first. Wait, this is yesterday. Something is not right. Isn't this from yesterday? No, this is not from yesterday. Come on. I don't know what you're thinking. I think everything's right. 5556, yeah. Yesterday is... Actually, let's do ST. This is yesterday. Max vowels, yes, that's yesterday. This is not. This is... Yeah, I was thinking about vowels. So yesterday is vowels. I thought that was yesterday. No, it's not. All right, so what we're gonna do is we're gonna sort this one first. And we have a J, len nums -1, okay? Then the rest equals 0 for I and enumerate nums, all right? Then what do we say? What we say is while nums j, while nums j is larger than target minus n, right? When it's larger than this, j minus equal 1. And once they get out, that will be the first one that nums j is smaller or equal to. Okay, then we can say res equal to res plus 2 to the power of what? From j minus I, right? J to I. 0, 1, 2. I have 2, yeah, so that, and we'll mod. Right, and we'll do this and mod. And we keep going until what? until so j has to larger while I is larger or equal to j, and right I is smaller or equal to j. When I get out and we say if I is larger than j, then we'll break out. Then we'll return res. Okay, let's try this. First one is 4. Second one is 6. Third one is 61. Okay, here is nums target. Nums target. Okay, correct. Let's give this a shot. Let's run. Target is 1. I don't know, just random target. Or we can do this. Right? Including everything. Yep. I shall do it. Come on. This is a problem. Okay. It's just slow. I wonder if I mean, technically this is on, because this going back only once. Like, basically it's 2 pointers, right? We're talking about 2 pointers. This is 2 pointers and meet in the middle. But why would it still be so slow? Because of the mod? I seriously don't think so, but... Oh, I see. The power, Python power, the power function. Where is the documentation? I think it's the built-in that we want to look into, right? Power. Yes, you can have mod. Return base to the power if mod is present. So, yeah, I know. So what we're gonna do is, we are going to mod it. Power. No, it's a pow, right? It's pow, it's not power. Pow. Kapow. It's pow. To the this power. And we'll mod. And I'm pretty sure we can plus equal to, and then just do the mod at the end. All right. This is performance, a boost. Okay. Let's see how much. Oh, oof, oof. Performance. I was stuck in my research today. It's also about performance. I have a fingerprinting method. I mean, basically just wrote a KNN from scratch, but dude, that one is slow as hell. I have testing like 73,000 testing cases. And I run through that. It took like 111 minutes. It's like, nah, that's not gonna work. Yeah, you gotta find some way to get the performance up. And this is just little things, right? Since it is subsequence, we can sort nums. Then for each value from left to right, we can find all the subsequences that starts from that value. Since that value is the main, we just need to use target minus min to find the max allowed value. Then we search in nums to locate where is the max value that is smaller than the max allowed. Then all the numbers in between the max value and min value can be attached to the min value. We can use binary search to locate the max value that is smaller than the max allowed, but a two-pointer method is more efficient. Furthermore, the count of available subsequences is power of 2. Since the power can be huge, we need to use the pow function to mod while performing the power. And I remember, and there are ways to do it, but I don't. Yeah, I always struggle like to handwritten the power. You know, the faster way to do power. I always struggle that. Yeah, don't think about it. But that's that. So it would be on. What's this? This is a log, right? This is a log. Huh. Interesting. What is this? On times pow. Whatever pow is. It should be a log of this. So I think I can say it's on log n. Oh, it's on log n anyway, because I have the sort at the beginning. So yeah, no hard feelings. On log n. Alright. Now it's time to check the solution. Binary search. Yes, you can always do binary search. 2 pointers. Yes, you can always do 2 pointers. Let's just check. Oh, that, yeah, that's good. That's good. It's like more 2 pointers, right? It's like absolute 2 pointers. There's a 2 pointers too. But, Well, this is a cleaner. I have to admit, this is a cleaner. This is much cleaner. Oh, my login. Sliding window. Okay, so that's that. Now we need to read the solution from yesterday. This is not a medium. Oh, it was a medium problem. Prefix sum. I mean, it's not a prefix sum. It's a prefix product. All right, let's not see people's. Okay, what is your Dude, he factorized it. He factorized it. That's a neat trick. Very neat trick. This is just regular factorization. I think... what the hell is partial sum? Hold on, let's just see what his ideal is. Prefix, products of this and this are co-prime, and prefixes do not share any prime factors with suffix. Yes. Prime intervals. If element I shares the same primes as element j, we cannot split the array in ij interval. If this shares the same prime as element, so if 2 shares, then we cannot split the array in this interval. That is correct. In this solution, we identify all such intervals and look for a split point that does not belong to any interval. This is interesting. We record the first index of each prime. Then we use a number line to record the start and end of each prime interval. Finally, we do a line sweep computing the prefix sum. When the prefix sum is 0, we found our prefix sum. Using Sieve Eratosthenes, or you just copy and paste from online. I haven't written Sieves of Eratosthenes for a while. I might get a little bit rusty, but I don't think it's necessary for this problem. I'll just copy and paste. So we get the intervals, right? So that's what he's trying to say. We get the intervals for all of them that shares. Yeah, so if we split in between, that is not going to happen. So if we have something that's a start and then the end, if they share, that would never happen. So for each one, we need to find who shares with the first one. The largest one that shares with the first one, actually. Let's see, what's your factorized, okay. Line. Partial sum. Oh, that is, holy crap. I think is overlapping, right? This is overlapping. It's the same problem as scheduling time. Scheduling, right? scheduling. So you have the start, you have the end, right? So every time you hit a start, you add. Every time you hit an end, you minus. So from the start, wait, hold on. What you're saying? It's to find. Oh, and I think I know what he's trying to say. Line sweep. Oh, dude. I kind of forgot. So like, if you have interval, you want to find the first interval, that first position, that is. So you say if I hit this, right, we will +1. And we have another one, so this will be 2, and this position will be 1. This position will be 0. Yes. So you have the interval, so this will be 0, and here you'll be 1. So this is used to see. Yeah, I did this. I did this problem many times. Google likes this, by the way. I did, I think, 2 interviews with Google. They all have something similar to this. I mean, the actual problem is slightly different, but they all use this method. And you lay it out, and then when you hit the start, you add. Sometimes it's you count how many people. Sometimes you want to know. I think the problem, the latest one I did was, it give you a schedule. You want to find who is alone, who has his shift doing by himself or her, right? And it's basically the same thing, but you just need to use a set to record all the names, so you can know who is doing the job alone in which shift. So this is the same idea. Right? This will be the first time becomes 0. And that is where we can shift. Now, of course, I'm not sure what this partial sum is. I don't care. Why? Because line. This is the line, right? There's all the positions on the line. And line at this position hold on. We're looking at each value, right? We're looking at each value. And this factorize will give us all the factors. And I will go through all the factors. If I is an unordered map, right? We say if it's count equal to 0, which means what is if I? Factored index, right? So what you're saying is for each number you have factors. So we want to know to your left, right? That's what we want to know. What's the this is basically what's the first one that has this factor, right? That's what we want to know. The first index that have this factor. So we say, okay, the first that have this factor is this index. And if it's the first, then we're going to add it. And what is this? Because for you, you will always consider yourself at this position a delete. So you will minus yourself. I don't understand. Why you minus? I am... I don't know. I really have no idea why you would minus. We record the first index of each prime. We then use a number line to record the start and end of each prime interval. So if it's a start, we will increment. If it's the end, that is an end, right? And this position is an end. So every factor, this will be an end. This is a line. At each position, if it's a start, we add. If it's the end, we minus, right? And it is an end. If you think about it, it is an end. It's the current I for each factor. This is the position that you end. So you just minus 1. So you end here, right? Now every value it can serve as an end. Oh, lordy. Lordy, this is good. All right, let's try to implement it. Of course, we'll do something similar here. I think my solution is pretty neat. It's slow, but neat. Okay, so factor. Don't do counter. I just need to return a list of integers. Okay. All we need to do is factor it. So primes are going to be this. Limit. I'll pay this. If this break, otherwise, well, this might not do set. No. Well, I need to mention this is inspired by this. The key idea is to find the interval ij, to find all the intervals ij such that nums I and nums j share at least one prime. Then any splitting point within ij, within not including I, but you including, wait, do you include j? No, we say I and j. So if we split in the middle, so we have this. If we split on an I, yes, but we can split on j. If we split on j, then it doesn't matter, right? So within I to j, j is an open, right? Will not lead to coprime. Now after finding all the intervals, we just need to locate the first index that is not in any of the intervals. Now this can be solved using the same approach as finding overlapping intervals, or what the author of the post called line sweep method. We increment on the beginning right, of each interval and decrement on the end of each interval. Then in the prefix sum, first position that evaluates to 0 is the answer, is the first location, first index that is outside any intervals. Okay, so this, we have the limit for p in this, if n is equal to 1, or p is larger than the break, otherwise, we say if n, p is equal to 0, then primes dot append p. And while this, done, coming back up, if it's larger than 1, then primes dot append and return primes. And then we can say lines. That is actually a good thing. Lines equals 0 times len nums. Okay. And when you say first index of factor equals a dictionary. Say for I and enumerate nums. Okay. Then for f in self.factor, and for each factor, we say if factor is not in first, then first f equals I, right? And then we can and then this current value can always serve as the beginning of an interval or end of the interval. Right? Because we have we'll get the first, because whatever I am at, I consider this, right? I consider this to be the end. Right? I consider this to be the end, right? So I say we consider n to be the end of an interval. Then we look, we obtain the start position of the interval via first index of factor. Shared factor, right? So we say lines, first this f will be plus equal 1, right? So increment on start, and lines I minus equal 1. Decrement on end. For the current factor, right? For the current factor. For each prime factor. So yeah, so we do this, when we're done, then we shall do I mean, we probably can just pre-sum, right? PS, pre-sum is 0. Say for I, L in enumerate lines, PS plus equal to L. If PS is equal to 0, then we return I. Otherwise, we return minus 1. Let's see if this one's right. So the solution 2. I don't know what happened, man. We fail some, we pass some. The -1s will fail. That's interesting. Okay, let's see. What is lines for this one? Huh. Oh, I know why. Because it goes to the end, right? We're gonna break. And then we return I if I is smaller than line nums, else -1. Wait, isn't this one I is towards the end? The hell? Oh, smaller than this -1. Dude. There we go. That's the one. Okay. Ooh. Oh no, this one is, we solved that one. This should be much faster. Oh, look at this. 10 times. 10 times. Dude. 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 Well, factor is log n, so we call it O(n) log n. And this is O(n) as well. Dude. Isn't this the right answer? It is the answer. Dear Lord. It is a 10 times speed up. Intervals. Intervals. Two ideas, right? You have the intervals, and you also need to do this line thing. I need to memorize this line stuff. Beautiful, beautiful problem. All right, that will be it. I think so. I think I can just, yeah, I can close all of this. I have all these open. I just keep this out. All right, that'll be it. The next one will be another hard, so I'll do this tomorrow. I'll see you guys tomorrow. Adios.